Hello, everybody, and welcome to our next chapter. This is going to be a bit of a hybrid chapter. We're combining chapter 7 and chapter 8 together into one chapter. To me, it doesn't make sense that the book splits them up, and I think that they should be together. And so the two chapter topics are exponential functions and logarithms. So today we're going to be starting with logarithms and logarithmic functions, and we're going to learn about the laws of logarithms. So first, you're probably wondering, what's a logarithm? If you've taken chemistry, you might have already been introduced to this idea. Otherwise, this might be totally new. So let's say we want to solve this equation here. 250 equals 132 times 1.01 to the power of n. We saw things like this in our geometric sequences and series chapter, and our only way to solve this was guess and check. We would have divided both sides by 132, and then we would have just started plugging numbers in for n until we got something that worked. Now, first, that's tedious and slow and doesn't make sense that that's the only way we can do this. And second, what if n is not a nice number like 5 or 2 or 7? What if it's something like 3.02051? That's not going to be something you're going to be able to guess. We could also graph this and graph the left side as one equation, graph the right side as another equation, and see where they cross and find our n value that way. But again, these are not very nice numbers. So to graph that by hand seems a little bit ridiculous. So our last method is something called a logarithm. So for example, we know 2 to the power of 4 is equal to 16. But what if someone asked us 2 to what power equals 16? Well, a logarithm would help us find that missing power. So a logarithm is a few things. One, it's an easy way we can express very large numbers. Two, it can be thought of as a type of exponent. And probably the most important is it can be thought of as the inverse of an exponential function. So how do they work? Well, if I was saying log 10 and I want to know what this equals, what I'm really asking you is 10 to what power equals 10? Well, 10 to the power of 1 equals 10. So my answer here would be 1. If I asked log 100, what does that equal? 10 to what power gives me 100? Well, 10 to the power of 2 gives me 100. So log 100 is equal to 2. What about log 1000? Well, again, 10 to what power gives me 1000? 10 to the power of 3 gives me 1000. So log of 1000 is equal to 3. So all of these that we just wrote, we could keep going if we wanted, are in something called base 10. And that's because the base of the exponent we're talking about is 10. And your question might be, well, how did you know that was your base? And it's because technically hidden down below at the bottom of the G here is a little invisible 10. So when we don't have an actual number written here, we assume we are in log base 10. Okay? It does not need to be base 10. And that's because why would we always be looking for exponents or powers of 10? The question above, the base was 1.01. So base 10 is not always going to work for us. If I wanted a different base, I would have to write in that little number by the G. I would write something like log base 4 of 4. This tells me my base is 4. And so I'd be asking 4 to what power gives me 4? Well, 4 to the power of 1 gives me 4. So this is equal to 1. If I had log base 4 of 16, I would be asking 4 to what power gives me 16? Well, 4 to the power of 2 gives me 16. So this is equal to 2. And again, I can keep going. Log base 4 of 64 would be 3 because 4 cubed is 64. So these ones here all have a base of 4. So hopefully you can notice a little bit of a pattern. Okay? The base of the log is the base of the exponent. So if I have some log with any base a, and I have some number b as the inside stuff of my log, and this equals some number c, if we wanted to change this into exponential form or vice versa, we can see that the base of the exponent is still a. Notice how these are all 4s here, and these are all 4s here. That's my a in my log base a of b equals c. Hopefully you notice that all of these numbers here, the inside stuff of the log, or the b in my black formula there, is what my exponent equals when I'm done. And hopefully you notice that the exponent in the exponential form is what the logarithm equals when we're done. So that would be in the black stuff over there, log base a of b is equal to c. C is the exponent in the exponential form. Oh, let's make that the same color. So these two things are equivalent. So we can convert back and forth between these two forms easily. So A is your base. So it's both the base of the exponent or the power form and the base of your log. And you'll notice that the C value here is your exponent if you're in exponential form, and it's what the log equals. So the log and the exponential form are inverses of each other, and they're an easy way to be able to figure out what does that missing exponent we don't know equal. So today we're going to be working with logarithms. So the algebraic definition of a logarithm is what we just wrote. Okay, so you can write it again if you want, but you don't have to. So log base a of b equals c is equivalent to a to the power of c equals b. Now a note that your base must be positive and your base can't equal 1. Because if our base was 1, if we had log base 1 of 1, we don't know what the exponent is, because 1 to the power of 5 is 1, 1 to the power of 20 is 1, 1 to the power of 52 is 1. We wouldn't be able to find c. We can't narrow it down. So your exponent cannot be 1. We're going to try a couple of these. So if I had log base 7 of 49, what I'm really trying to figure out is 7 to what power gives me 49? Well, 7 squared gives me 49. So log base 7 of 49 would equal 2. Log base 4 of 64 we just did. That's 4 to what power gives me 64? Well, 4 cubed gives me 64. So log base 4 of 64 would equal 3. Now, these ones would be considered very straightforward logarithms because they are nice, neat powers that you can figure out by just looking at these. But what about something like log base 5 of root 5? Well, we need to pull back our exponential rules from grade 9 and 10. And we need to remember that if you have any radical, that we can rewrite that as a fractional power. So we know that root 5 is the same as 5 to the power of 1/2. So this is asking 5 to what power is equal to 5 to 1/2? Well, the answer would be 1/2. Now the next one, we have the fourth root of 27. Okay. Well, first we know that we can rewrite this as 27 to the 1/4 using our exponent laws from grades 9 and 10. Because the index on the radical is 4, our fraction would be 1/4. The previous one was a square root, so our index was 2. That's why we had 1/2. And the problem here we have is that we've been asked 3 to what power gives me 27 to the 1/4. Well, it's not easy to tell by just looking at this, but I know that 3 cubed is 27. So I could rewrite this as 3 cubed to the 1/4. Now, again, using my exponent laws from grades 9 and 10, I know that if I have a power of a power, I can multiply the exponents, giving me 3 to the power of 3/4. So the question is 3 to what power gives me 3 to the power of 3/4? Well, we can see here my exponents on my two sides must be equal, so my question mark must equal 3/4. Now, as you get going on some of these, you will get faster at these and you won't need to go through so many steps. As soon as you see the base is 3 here, we want to rewrite it, the 27 cubed root, or quartic root, sorry. We want to rewrite that 27 as a base of 3 as well. So notice how when we had a base of 4, we rewrote it as 4 to the power of. The base of 5, we rewrote as 5 to the power of. The base of 3, we also want to rewrite as 3 to the power of. Okay. So this last one, we would be asked a to what power gives me 1? And the answer is 0, because any number to the power of 0 gives me 1. Now, if we want to go in the opposite direction here and change forms, okay, what if I gave you the exponential form and I just ask you to write it in logarithmic form? So this is where we are going to need our little equation from the other side of the page. So basically, you need to identify what is your A, your B, and your C. In this first one, my A would be 5, which means this is going to be log base 5. My B would be 125. So the inside stuff of my logarithm would be 125. And my C, my exponent, is 3, which means my logarithm equals 3. And this would be considered a very basic one. The next one, the base of the exponential form, our A, is 3. Our exponent, or our C value, would be -3. And our B value, or the inside stuff of our logarithm, would be 1/27. So we're just taking a look at our equation in the black square, and we're saying, okay, what is our A, our B, and our C? And we're rewriting it in the opposite form. For this last one, there are no actual numbers. We're just replacing letters with other letters. So as you can see, our A is still an A, our B is now a Y, and our C is now an X. And this is used quite commonly. So in the PDF copy of the notes online, this is the equation that I've used instead of A's, B's, and C's. I've got A's, X's, and Y's. It doesn't matter what letters you use. We could use smiley face, unicorn, and a star. The important part is that you understand that the base of the exponent is the base of the log. the exponent in the exponential form is what your log equals, and the answer in your exponential form is the inside stuff of your logarithmic form. For number 3, we are doing the same thing. We're just transitioning forms. We're not finding what anything equals. There are no unknowns here. We're just switching what the form is. So again, you can reference this formula that we have here. So in the first one, we can see that our A value is 3. That means the base of our exponent is 3. Our B value is 27. That's what our exponent is going to equal. And our actual exponent, C, would be 3. 3 to the power of 3 is 27. The next one, our base is 5. Our exponent is our C value, which we can see from our equation in black here is actually -2. And 5 to the power of -2 equals 1 over 25. Again, the last one, we don't actually have any numbers. We're just rewriting this using our knowledge of what goes where. Our base is A. Our exponent would be X. And our inside stuff is what our exponential equals, which is. You do need to be able to transition between exponential and logarithmic form. There's some questions for practice you can do for those. And once you get the hang of them, they're quite quick. Now, the problem we have is that those are all nice, neat answers. We don't always have a nice, neat answer. So we will learn how to be able to figure these out exactly. But for now, if we wanted to estimate, we would have to use a bit of logic and reasoning here. So the solution here, we're trying to find 4 to what power gives me 90. Well, I know that 4 cubed is 64. And 4 to the power of 4 is 256. So first, what are we closer to? Well, we're closer to 4 cubed. So we know that this isn't 4 cubed because this doesn't equal 64. It equals 90. So it would be a little bit bigger than 4 cubed. But it's definitely closer to 4 cubed than it is to 4 to the power of 4. So we could say approximately 4 to the power of maybe 3.2 is equal to 90. And you could actually try that on your calculator. If I do 4 to the power of 3.2, I get 84. So I would need to go a little bit higher. What about 4 to the 3.3? I get 97. So I need to be somewhere in between there. So I'm going to say 4 to the 3.25 as my guess. And that gives me 90.5. That's a pretty good guess. So I'm going to say this equals approximately 3.25. Now we can do the same logic with the next one. I'm figuring out 6 to what power is 1 over 200. So again, using our rules from back in grade 9 and 10, we know that this should be a negative exponent, right? So 6 to the -2, for example, is 1 over 36. 6 to the -3 would be 1 over 216. And again, using our laws from grade 9 and 10, we know 6 squared is 36. And that's where I get 6 to the -2 is 1 over 36. 6 cubed is 216. So 6 to the -3 would be 1 over 216. Again, we're much closer to -3 than -2 here. So we could guess approximately maybe 6 to the -2.8. And if we try that on our calculator, now the problem is going to be with the way most of your calculators work, this would give you a decimal answer if you do this. So it might be helpful to figure out what is 1 over 200 as a decimal. We get 0.005. That's what we're trying to get close to. So if I do 6 to the power of -2.8, I get 0.0066. So not bad, but I want to be a little smaller. And so remember, if you're dealing with negative exponents, that means my exponent needs to get bigger. So I'm going to try about 6 to the negative 2.9, and let's see what that is. And that's what I get if I plug that into my calculator, which is pretty close. So I'm going to say that's a good enough answer. So this is approximately negative 2.9. So for ones that aren't exact, if it says estimate, you're not totally in a guess and check situation because you can use these barriers on either side of things that you do know, but you're a little bit in a guess and check situation. If it says estimate, there is a mathematical way we can actually figure this out that I will be showing you later on today. Okay, so if you were asked to actually find out what these are exactly, we can do that. So if you're feeling like this is enough for you today, you could stop here, go try some practice questions where you're just converting between the two forms or identifying the base, the exponent, and the answer, or the base and the inside stuff of the log and the answer. You wanted to go and try that now, you could. If you're feeling like, nope, this is making sense, I'd like to keep going, then keep going here. We're going to be looking at some logarithm laws. So these are ways that logarithms interact with each other and how we can split them up to make them a bit nicer and into more perfect values that we can easily find out so that we don't end up with gross answers like we just saw. So the power law is our first one. This says if you have log base A of some value x to the power of m. So the x to the power of m is all inside the logarithm. The logarithm is not being put to that power, just the inside stuff is. And with a logarithm, you're allowed to bring that exponent down in front and rewrite this as m times log base a of x. Okay. So for example, let's say I had log base 2 of, let's say I had 4 cubed, I could rewrite this as 3 times log base 2 of 4. And I know log base 2 of 4, 2 to the power of 2 equals 4. So this would give me 3 times 2, which would equal 6. The product law says if you have log base A of some m times n, you can rewrite this as log base A of m plus log base A of n. So for example, let's say we had log base 2 of 4 times 8. We could rewrite this as log base 2 of 4 plus log base 2 of 8. I know log base 2 of 4, 2 squared is 4. 2 cubed is 8. So this would give us 5. The quotient law is if you have some log base A of m over n, you can rewrite this as log base A of m minus log base A of n. So again, if I use these base 2s still, if I do log base 2 of, let's say I had 32 over 4, this is the same as log base 2 of 32 minus log base 2 of 4, which would give me 5 because 2 to the power of 5 is 32, minus 2 because 2 to the power of 2 is 4, which would give me 3. Now, in all of the examples I've just shown you, you could do these without the log laws because if you actually try, for example, the one we just did, 32 divided by 4 is 8, and we know log base 2 of 8. So we could have actually done that without these log laws. These were just used to show you how the rules work. So also just a little note in case you didn't remember from the first page, if you don't see a base, there's no base specified. The base is 10. So on your calculator, you actually have a log button. That log button will default to a base of 10. Some of you with super fancy ones, when you push the log button, a little box comes up, like where my A is here, and it makes you type in that base every single time. But most of you, if you have the special calculator with the little box, you have an option that has the box, and then you also have a very basic log button that doesn't have the box that'll default to your 10. So we're going to try some questions where we use these log laws to split things up and make them a bit easier to solve. So for example, if I wanted to do log 8 plus log 125, well, log 8 is not something that we can do nicely. So don't write this down. I'm going to erase this in a minute. Log 8 equals what? Well, what we're trying to figure out here, this would be technically log base 10, and this would be 10 to what power equals 8. There is no nice power we can figure out where 10 to that power would be 8. It doesn't exist. It would be a really gross number. So instead, we can simplify this equation using our log laws so that we have a number we can do nicely. So because we have a plus here and we have two separate logs, we're dealing with product law from before that has already been split up. So if I want to put this back together using the product law, it says that if we have two logs of the same base that are adding together, we can rewrite this as a log with that same base where the insides are multiplying. Again, we don't have to write 10. You can, but this is a log base 10. Now, if I actually multiply 8 and 125, I get 1,000. And so what I'm trying to figure out is 10 to what power gives me 1,000? Well, 10 to the power of 3 gives me 1,000. So this would equal 3. The next one, we see a subtraction. We've got two logs with the same base subtracting, which if you look up in your box above is our quotient law. We can rewrite this as one log with that same base, which for us would be 6. And then we can divide the insides. So the first one is 90, that goes on the top. The second one is 2.5, that goes on the bottom. If I actually divide these, I get 36. And so what I'm really trying to figure out is 6 to what power gives me 36? 6 to the power of 2 gives me 36. So this equals 2. Last one. Again, we've got subtracting. We've got two logs with the same base, so we can write this as one log with that base. We would have 5 over 20, so it's not just the biggest number over the smallest number. It's whatever's in front of the subtraction goes on top, whatever came after the subtraction goes on the bottom. So we would rewrite this as log base 2. I would simplify this to be 1 over 4. So what we want to know is 2 to what power gives me 1 over 4. Again, we know that if we have a number on the bottom of a fraction like this is a negative exponent. So 2 squared is 4, which means 2 to the negative 2 is 1 over 4. So this is equal to negative 2. So if you do not have negative exponents fresh in your mind, if you don't remember that those are essentially a reciprocal, I would suggest that you maybe go back and review that. Our next one, we are being asked to express as a single logarithm. So our only goal here is to fix everything up so that we can rewrite it in one log. So we're undoing all of our log laws, essentially. We always want to start with the power law first if we can, and then move to product or quotient. So the first thing I want to deal with is the fact that I have these numbers in front. So the power law was if you had log base A, son x to the m, this was the same as saying m times log base a of x. So we have it in this format here. So our m in this first one is a 3. Our a would be 10. There's no base written, so we assume 10. So I can rewrite this first term as log base 10 of x to the 3. I can bring that outside number m back up and turn it back into this form. I can do the same thing with the next term and bring that 2 back up. Now I would need to combine these together using our product law. So we can see we have 2 logs with the same base. The base on both of these is 10. They're adding, which means if I want to rewrite it as one logarithm, I would need to multiply the insides. So this is going to be rewritten as the log of x cubed y squared, multiplying the inside stuff together. I can't actually evaluate this. It didn't ask me to. It just said express as a single logarithm, which we have done. We're done the question. The next one, same thing. I want to deal with any of my power laws first. So any numbers in front of the log, I want to bring those back inside the log where I can. So the first term is going to stay the same. There is nothing in front to bring up. The next one I would rewrite as log base a of y cubed, bring that 3 back inside as an exponent on the y. And the last one, same thing, I'm going to bring that exponent up onto our z or z. Okay. Now I can deal with the fact that we have a product law from the plus and a quotient law from the minus. It doesn't actually matter what order you go in. We know that the x and the y are going to be multiplying because of that plus there, and the z squared is going to be dividing because the minus is in front of that term only. So you can do this all at once, or you can work left to right. If you work left to right, we'd be doing our multiplying first, which would be xy cubed. If I rewrite the plus using our product law, and then for now, I would still have our minus log a base a z squared. Now last, I can actually use my quotient law. So because my m term, if I look at my box from above, this guy here, my m, is this entire term xy cubed. So I'm going to rewrite this as log base a xy cubed over z squared. Again, we can't evaluate. We have no numbers here. Okay, we're going to leave it like this. This is a single logarithm. You could have gone straight from this first line we wrote straight down here. That would have worked as well. You don't have to go in 2 steps. If you want to jump straight to that end bit, you can. Now, this last one's a little tricky. This would be considered like a hardest type of these questions on a test or a take-home assignment. Part of the reason is because we've been asked to write as a single logarithm, but we don't have more than one logarithm. We only have the log base 4 of 7. And then we have this mysterious minus 2. So what we really need to do is we need to rewrite this 2 as a logarithm. And the question is, well, how do we do that? Well, I know that I need to have a log of base 4 because the question has a log base 4. And I need to figure out what needs to go inside of that, but I know it's supposed to equal 2. Well, if I change this to exponential form, I know that 4 to the power of 2 would have to equal the inside stuff of my logarithm. Well, 4 to the power of 2 is 16. So that means that if I want to rewrite 2 as a logarithm with a base of 4, I would need log base 4 of 16. I'm going to rewrite this. I'm just running out of space a little bit. I'm going to say that this is log base 4 of 7 minus log base 4 of 16 because log base 4 of 16 equals 2. So I've replaced the 2 with something else that still equals 2. And then I can use my quotient law to rewrite this. Again, it did not say evaluate. We can't evaluate this because log base 4 of 7 is not a nice thing. It just said express as a single logarithm. That's it. Okay. So all of these questions that we've just done on this page, we've used our log laws to put all these different logs back together in one statement that is possibly easier to evaluate if you're looking at 1, 2, and 3, or at least simplify it if you're looking at the second set of number 1, 2, and 3. Okay, so being able to put all these separate logarithms back together into one is a good way to simplify things. We can also use these log laws to expand things back out. So we're going to try some of those next. So these questions, we've been asked to express each of these expressions in terms of a log A, log B, and log C. In other words, spread them back out so that one of your terms only has log A's, one of your terms only has log B's, and one of your terms only has log C's. Okay, so we want to split this all up using our log laws. So when we split things back up, we're going to deal with product rule, quotient rule first, power law last. So maybe I'll write this down for you. Okay? If you're using log laws to simplify, like we did on the previous page, deal with power law first, then product or quotient law. If you're using your log laws to separate things out and expand, like we're about to do, then you're going to deal with product or quotient laws first and then your power law. So because we're doing opposite things, expanding versus simplifying, we want to deal with the laws in the opposite order. Okay. So for this one, we wouldn't, for example, bring the 2 down in front of the log first from that a squared. And that's because the 2 is only on the a. It's not applying to anything else inside the log. So we can't bring those exponents down before we start because they're only applying to certain pieces of the inside bits. Okay, so I want to separate this up using my product law first, which would mean I'm going to get log a squared plus, because a squared is multiplying with our next thing, which would be a b. And then we're multiplying with the c cubed, so we're going to do that one last. So a squared is multiplying with a b, which is multiplying with the c cubed, which means we can separate this into 3 separate logs that are all adding together. Now that we've done that, in the first term, we can bring that 2 down in front. The log b has nothing else that we can do here, so we're going to leave it. And the last one, we can bring the 3 down in front to be 3 log c. And that's it. That's all we have to do. We're done. The next one, we would have log a cubed minus, because we're dividing, and we're dividing by this entire bottom bit. So I'm going to put this in brackets. We're dividing by log b squared c cubed. We're dividing by this whole thing. Now the b squared c cubed, we've got things multiplying there. So we can further split that up. And again, some of you will do this in one step. That's fine. So I would have log b squared plus log c cubed, because the b squared and the c cubed are multiplying with each other. But notice that the a cubed is still being divided by this whole bottom bit, which means we need to subtract that whole log b squared plus log c cubed bit. So we can't write this, again, don't write this down. We can't write this as log a cubed minus log b squared plus log c cubed, because this would indicate that you're dividing by b squared, and this would indicate that you're multiplying by c cubed. But you're not, you're dividing by c cubed. And that's why you either need to keep this in brackets, you want to expand the minus in, you can, but then if you do that, you would actually have a minus here. Okay, so if you want to expand your brackets, you are welcome to, but you need to have a cubed dividing by b squared and c cubed, which means your log of a cubed must subtract log b squared and subtract log c cubed. Now we can bring our exponents down. And all of our terms have exponents. We can leave it like this, or we can expand that minus in. Again, some of you will do this in one step. The more of these you do, the faster they get. And the more of these you do, the less steps you'll need, really. Some of them will require lots of steps no matter how many you've done, but hopefully it'll get a little easier as you go, okay? So these next two, we actually want a numerical answer. We want to try and find an actual number answer. And so if we can evaluate from the get-go and then add and subtract things, great, but usually on these questions you can't. So for example, if I wanted to do log base 9 of 6, I'd be asking 9 to what power gives me 6? Well, again, nothing nice. So we want to use our log laws to combine these logs into a nice expression. Same thing here, 9 to what power gives me 72? Nothing nice. So we want to try and combine this together to give us a nice answer, something that we can evaluate nicely. Okay. So again, we want to simplify these together. So we're going to deal with power law first, then our quotient law. So I'm going to rewrite this as log base 9 of 6 cubed. I'm going to bring that 3 back in, minus log base 9, 72. Now I can deal with my quotient law. If you'd like to figure out what 6 cubed is and write that in, you can, or you can go straight into your quotient law and say log base 9, and this would be 6 cubed over 72. And now I'm going to plug this all into my calculator and figure out what I get. 6 cubed divided by 72 gives me 3. So I want to know what is log base 9 of 3. And so when I find this answer, my question is 9 to what power gives me 3? Well, I do know that the square root of 9 is 3, and the square root of 9 would be 9 to the power of 1/2. Okay. Which means that log base 9 of 3 is equal to 1/2. So this whole expression here is equal to 1/2. Now, some of you will have calculators that can do this for you. Obviously, that's not the point. So on something like an assignment, or if we were in class, a test, I don't care that your calculator can do it. I want to see the steps. The purpose of asking a question like this would be, do you understand the log laws? Do you know how to combine things together using the log laws? The fact that it equals 1/2 is really inconsequential. I want to know that you understand you can bring that 3 up as an exponent on the 6, and that you can divide the 6 cubed and the 72. That's really what I'm looking for here. We'll try one more. Again, log base 4 of 6, not a nice answer. Log base 4 of 3, not a nice answer. We're going to use our power law first to bring the 2 that's in front of the first term and the 3 in front of the second term up. So this is going to be log base 4 of 6 squared minus log base 4 of 3 cubed plus log base 4 of 12. Again, if you would like to actually rewrite this as 36 and as 27, you can. You do not have to. Now our log laws, we've got 2 log laws here. We've got that 36 must be dividing by 27. and multiplying with the 12. So when I rewrite this, I've got log base 4. I've got 36 over 27 times 12. Okay. Now, if you didn't do that, if you had not simplified, you'd have 6 squared over 3 cubed times 12. So on my calculator, I'm going to punch that in, and I get 16. And I know that 4 squared is 16, so this equals 2. Okay. Again, if you have the fancy calculator that can do the other bases easily and type this all in and get 2, it's a great way to check your answer, but I don't really care that it equals 2. I care that you were able to figure out that that inside bit was 16. I care that you knew that the 2 and the 3 as exponents went back up. I care that you knew that 36 was divided by 27. You were multiplying by that 12 and not dividing by that 12. Okay, so again, on a take-home assessment, or if we were in class on a test, it's the steps I'm interested in. It's not the answer. So the last thing for today is for those of you who don't have the fancy calculator, it's a way that you can do what's called change of base. So for example, if I had something like log base 3 of 7 or log base 9 of 0.5, we can actually figure out what these equal exactly with decimals, instead of having to guess and check like we did on one of those previous questions that we tried on the second page. So change of base looks like this above business. So log base b of a is equal to log base n of a, where n is any base, over log base n of b. So those of you who don't have the fancy calculator, usually your n is going to equal 10 so that you can use your log button. Okay, so some of you should all have a log button. Some of you will have one that looks like this. Those of you who have one that looks like this, you can just type this in. You can put 3 in this little box here, and you can put 7 in this box here and hit equals, and it'll tell you what the answer is. Those of you who don't have this button, you might also have one that looks like this. Okay. If you have neither of those and you just have this guy here, you're going to need this change of base. Okay. So how you would do this is you would rewrite log base 3 of 7 as log 7 over log 3. Notice that this is not equal to log 7 over 3. Okay, those are not the same thing. Log 7 over 3 is log 7 minus log 3 from our quotient law. It is not log 7 divided by log 3. Okay, there is no way you can simplify this. But you can type this into your calculator. You can type in log 7 divided by log 3. And if you do that, you get approximately 1.77. So try that in your calculator if you don't have the fancy button. Okay. This next one, we would write this as log 0.5 over log 9. We would type that into our calculator, and you should get approximately negative 0.315. So again, if you have a fancy calculator with the little boxes or the X and the Y, you can just type it in as you see it in the question. You should get the same answer. Some of you, when you type in your log button, it'll do this. This is what it does. So you need to make sure you end the bracket before you divide, and then you do the next one, end the bracket, and then hit. So make sure you're comfortable with your calculator. Some of the phone ones are a little finicky, so if you are using a phone calculator, especially try some of these questions and make sure you know how to enter it in. But this is a fairly long lesson. The questions won't take you that long to actually try. They get quite repetitive, so do however many you need to do. There's lots of extra practice posted for you as well if you'd like, in the practice stuff folder and then in the extra practice folder within that.